So first thing we know, force is a vector quantity, right? What is a vector, right? That means it has direction and magnitude, right? That comes into play in every unit. Pretty much the first day of every unit, we talk about vectors and scalars again. Right, force is the ability to change, cause a change in the state of motion of an object, right? If you want to get basic, like, you know, fourth grade, it's a push or a pull, right? Anything that pushes or pulls is exerting a force, right? But the important part is it's a vector quantity, it has direction, and it has magnitude, meaning it has a size to it, and you're applying the force in a certain direction, which is then possibly keeping it in equilibrium, at rest, moving at a constant velocity, or causing it to accelerate because it's an unbalanced force. Right? That's pretty basic, straightforward stuff. Probably same stuff that, you know, like 7th grade, 8th grade science is learning. We use the symbol F, which makes sense. Now, but the problem is, though, we have so many different types of forces. And so if we're going to use F, we're going to need to use a lot of subscripts. Otherwise, you're going to get lost. But you'll see that sometimes certain forces, we use the capital letter for what that force is instead of using F. And so you can do it either way, and you can mix and match and do it part one way, part the other way. The unit is a Newton. Now, this is important because a Newton is our first, what we call derived unit, right? So a derived unit, let me see if I can annotate here. So a derived unit means you're combining multiple units to get it. So if you have a kilogram times a meter over a second squared, that is equal to a Newton. Now, if you dissect that, right, you have a unit of a kilogram, well, you know that's a unit of mass, and you have a meter per second squared, right? That's a unit of acceleration, right? So that kind of gives you the idea of where F equals ma, which I assume you've probably heard of. M times A equals force, right? And so it's derived because you take the meter, which is a base unit, you take the second, which is a base unit, and square it, and the kilogram, which is a base unit, and you combine them in this manner to get a Newton. So this is really our first derived unit, because everything else has been meters per second, and meters per second squared. Right, and so it's important because what happens is as we keep going into momentum and we go into energy, units start to combine to make other units, like the joule or the watt. Like a Newton times a meter makes a joule per second makes a watt. So I mean, in the overall scheme of units, AP Physics 1 doesn't really get past first grade, and so you really don't have a lot to learn in terms of units compared to what's really out there. But it's the first time where we've done that. Forces result from the interaction between two different objects, right? We have to have two different objects in order for these forces to, you know, have an effect. There's two different types. There's the kind that we call contact interaction. So there's certain forces where basically that means the forces, the two objects are in contact with each other, right? You're pulling, like Dallas is pulling Dakota's hair, right? There's Dallas and Dakota are the two objects, and they're in contact with each other, and Dallas is exerting a force on Dakota, right? The Earth is pulling on the moon, and the moon is pulling on the Earth. That's an interaction at a distance, right? The moon and the Earth are not touching each other, but they're still exerting a force. So all those, what they call interaction at a distance forces, are all the ones that have fields. And that's gravitational field, that's electric field, that's magnetic field. Anything that has a field exerts a force, but those things are not touching, right? All the others, friction, tension, compression, the normal force, any push or pull, where you have objects touching, those are contact interactions. Oop, I can get rid of my annotation. Or if you're, I don't know who that is, but if you have that ability to use the Star Wars force, right, that would be interaction at a distance also. Now, we have this idea of we can use geometry to solve anything that's a vector. You can use things that you learned in geometry to solve these problems. We just don't do that, but you could. And if we had done the unit on vectors, which years ago used to be a unit that they've now just kind of taken away and said, teach the idea of vectors inside of all the other units. And it's kind of like if you go back to like if you were in Mr. Kearns's drafting class, where you do a lot of things where you're making drawings of things that are really big and putting them on paper. So you have to go to a scale. It's that idea, being able to take something and make a picture of it using a ruler and a protractor. We just do it mathematically. So forces are represented by an arrow, right? So we're still using this idea to make our force diagrams. Forces are represented by arrow. The tail of the arrow, so this is the tail of the arrow right here, is placed on the object that feels the force. So if this is my object and I'm pulling on this object, I put the tail of my force on the object. The arrowhead points in the direction of the applied force. So if I'm pulling to the right, then here's the object. I'm pulling to the right, the arrow points to the right because that's the way I'm pulling. The length of the arrow is supposed to give us an idea of the size of the force. So if I'm pulling this way with, say, a force of, say 10 newtons, right? And so what you could do is you could get out a ruler and say, okay, I'm going to make 1 centimeter equals 2 newtons. And then you would draw this 5 centimeters, right? And then what if Dakota is now pulling in this direction? Why did it do that? My little tablet here doesn't play really nicely with the new computer for some reason. Let's say Dakota is pulling this way, but she's only pulling with 4 newtons, right? And so I could draw this one 2 centimeters. That's the way we did in the vector unit if you wanted to make things to scale, right? And then we could say, okay, well, if I draw one this way and then Dakota's pulling this way, what is the resultant? Well, the resultant would be this, right? The length of that. We can just add and subtract and use some trig to do these answers. But the idea is if she's applying a force of 4 newtons, her representation of that force should be smaller than mine because my force is 10 newtons. Now, we're not going to get out, again, if we're not doing this using a protractor and a ruler, then we're just estimating that this is going to be 10 and this is going to be 4, right? If it was 5, you would just try to say, okay, visually make it half the size. But again, when you're making force diagrams, we don't have to make them exact, right? They don't have to be to a scale. But you could do that and you could solve most of these problems doing physics that way, is drawing things to scale. And then, sometimes you're going to end up with, right triangles or different types of triangles, but using a protractor and a ruler based on your scale, you could easily figure out these answers. But that's what we do when we represent a force by a vector. So we draw the line segment, we add the arrow in the direction of the force. We try to make it proportional to the size of the force. This is called the head of the force, the arrow, and it points in the direction, and the tail of the force is on the object. And when we add force, right, again, that terminology, we have what we call the net force or the resultant force. I like the word resultant, but not everybody does. And so when you look at an AP question or you read a textbook or something, you're listening to another video, they might use different terminology to mean the same thing. Basically, it's the sum of all the forces. That was loud. Now, how do I change? Nathan's coming back to us. Oh, wait, hold, hey, what do we got here? Function lock, what does that mean? Maybe that's what I needed. Ah, there we go. Now I can change the volume. This new computer has some new bells and whistles. Uh-oh, uh-oh. Huh. I also goofed that up. I don't know what happened there. All right, I think I'm back. So this idea of net force or resultant force, that just means the sum of all the forces. Now, what happens is when we get to Newton's second law, or even the first law, why is it doing that? Maybe I need to recalibrate my pad because, all right, let me try here. I'm nowhere near the edge of it, but it keeps thinking I am, I guess. So if you saw that, right, and you said, well, F equals 0, or you saw F equals MA, right? What people tend to think is that there's only one force acting on the, Nathan's having some computer problems. I keep getting loud buzzes in my ear.
Dad, you're not sharing the screen.
Oh, I'm not?
No.
Why didn't you tell me that like 2 minutes ago?
I did. I chatted you.
Oh, I don't even have the chat. That's why I don't see it. Hold on. You see it now?
Yeah, you're good.
All right. There's too many things going on. Nathan's getting kicked off here, having computer problems. That's buzzing my ear. My pad is not writing when I'm nowhere near the edge of it. It keeps clicking off. So when you see F equals 0, F equals MA, right? When you see it written like this, people tend to think, well, there's only one force, but that's not true. What this force represents, it represents all of the forces equaling 0, all of the forces equaling MA. I found that to be problematic for students. So I always write it like this, because whether you know it now or you'll learn it over the course of the unit, when you see sigma, right, this is sigma, that means sum. That means all of the forces equal 0, or all of the forces equal MA. But you'll also see it written F net, or you'll see it written FR as well. When two or more forces act on the object, their effects are cumulative. That means we're adding them together. But we have to add them together considering their magnitude and their direction. So that would mean if I'm pulling this way and here's the object and somebody is pulling this way, right? What we have to do is we have to figure out what is the, you see that? I'm on the edge and I'm nowhere, so my pad is not calibrated. So let me go over here. Right, if I'm pulling this way and somebody else is pulling up, to get the resultant, you have to add them like this, kind of like what we did with projectile motion, and this would be the resultant, right? This number, and that's how we add. Their effects are cumulative, so we have to add them together, taking into account their direction and their magnitude. And so we'll have two-dimensional problems because not all forces are going to act just in the X or just in the Y. But what we'll do is we will then apply this in the X direction and this in the Y direction, right, where appropriate, to get the different forces. And then we might, to get the resultant force, if that's what the question asks, again, we're going to go back to using Pythagorean's theorem. That's still a go-to for us to find the resultant. Now, we need to know what mass is, right? Again, this is a middle school idea. You learned it many, many times. Mass is the amount of stuff, right, matter that makes up the object. The symbol is M, and the unit is the kilogram, not the gram, right? In chemistry, you probably use the gram, but in physics, we use the kilogram as our base unit. And then this is probably, you're going to see so many multiple choice questions on this idea. Mass is not the same thing as weight, right? But in everyday language, if you're worried about gaining weight or losing weight, we use these words interchangeably when they're not really meaning the same thing, right? Mass is the amount of matter that makes up the object, where weight is the pull of gravity on that matter, right? And so, but that's not how it's spoken in everyday language. Your mass doesn't change based on your location, but your weight or your force of gravity does change based on your location. And so here on Earth, if your mass was 63.5 kilograms, your weight is 623 newtons, which is about 140 pounds. On the moon, your mass is still 63.5 kilograms, but now your weight's only 103 newtons. Why? Because the acceleration of gravity on the moon is 1.67, where here on Earth, it's 9.8. And so weight is based on what is the acceleration of gravity for your location. If you're on Jupiter, your mass is still 63.5 kilograms, but now your weight is 1,582 newtons, or the same equivalent weight here on Earth of someone that's 355 pounds, right? And if you went to the sun, your weight, 17,418 newtons, which is 3,914 pounds, which is 2 tons, right? A 140-pound person on the Earth, on the sun, if you could live there, obviously you can't, you'd weigh 2 tons, right? That's like a dump truck full of stuff, like rocks, right? Think how heavy that would weigh. That's how much you would weigh on the sun, right? But the idea is your mass doesn't change, your weight does change. Weight is based on location, and weight is our slang term for force. So types of forces. We have gravitational. This is like the 3 main headings. Gravitational force, electromagnetic force, and nuclear forces. Number 3 isn't going to come into play for us at all. We don't deal with nuclear forces at all. That would be AP Physics 2. That would be your chemistry class. Even AP Physics C, if you're taking that next year, you don't get out of the first 2. Obviously, the gravitational force is the one that you're most familiar with. And so pretty much you'll see that this is obviously one of the most important forces, but doesn't really have a variety of forces in there, where this has tons. Basically, when you look at macroscopic and microscopic viewpoints, then we get down to, well, that's really an electromagnetic force, because it's dealing with the interaction of molecules. So obviously, you know the first one, the gravitational force. So Fg, due to the pull of the planet on the object, obviously you're going to be on Earth and your entire lifetime, probably, unless you're going to be an astronaut and go to Mars or the moon, right? But the force of gravity is what we call the weight. And it has its own special equation, mg. I don't know why my G got cut off right there. It's on your formula sheet. It's actually written like this. And I've highlighted it because they've kind of hidden it. Why does it keep doing that? Right, or you can have W over G if you're using whichever term. It doesn't matter which one you use, but just understand that weight, W, is the force of gravity. It is a force. Mass is not the same thing as weight. But some of our forces have their own special equation. They're not all given on your AP formula sheet, but I will show them to you. That way, in case you write them down, you can remember them. But obviously, this is the most important one. It's an interaction at a distance force, because the Earth might be touching you and it might not be touching you, right? And again, we can use -10 or 9.8. Now we have what we call the applied force. This is a real general category for if you're like, well, something's pulling on this object, but I don't know what to call it. Well, you can call it the applied force, right? It's kind of like just a general term to represent any force acting on an object due to the object having something pushing or pulling on it. And so you might just call it F. I've seen people call it FA, but it might, as it says, it might be classified as, it could be tension, it could be compression, it could be any applied force. If you're pushing, somebody in a wagon, well, maybe it's a tension force, or maybe you're just applying a force, and we'll call it F. It's kind of like our general term to say, well, I know I'm applying a force, but I'm not really sure what to call it. It's the applied force. That's kind of a catch-all for us. right? So using a rope to pull an object might be called the tension, or you might just call it the applied force. So what is tension, right? So tension is my example earlier when I was talking about Dallas pulling Dakota's hair, right? She's got a bunch of hair there, and if you pull away from the object, right, that's tension. You put things in tension. If you take any project lead the way classes, I think POE, you guys do stuff with tension and compression and trusses, or maybe that's the second course, I don't remember. But as a civil engineer, you would be doing tons of calculating of tension forces and compression forces for steel beams and reinforced concrete and all those types of things, or even wooden structures. Tension is, and so we call it FT, or you can just call it T. It's an electromagnetic force because it's how the molecules are interacting with each other on both objects, right, on a microscopic level. But it's a ripping apart force, right? Here you got this guy standing on a wire, so we know that that's in tension. You tune your guitar, you loosen the strings or you tighten the strings, or same with a piano, right? You put more tension in it, makes a different sound. That's part of the waves unit. And then you see this one kind of shows you how this is a compression force, which is probably the next slide if I remember right. And then here's tension forces on the bottom. There's no special equation for it though, right? So you just have to know, like, hey, something's a chain, a rope, you're pulling on an object, that's a tension force, right? And then you have the compression force, right? Which is the exact opposite. Like if you have a headache, sometimes you put your hands up to your head and you kind of squeeze them together. Like sometimes that kind of makes the headache go away, right? You're compressing your head. You see it, again, here's your truss example. And then, if you got in a car accident, the steering wheel's compressing this guy's chest cavity because for some reason this car doesn't have an airbag. Those are compression forces, right? So it's the exact opposite of tension forces. You can use, I don't know why it's not there. You can use FC or C. Generally, we don't have a lot of compression forces in problems, but we do have a lot of tension forces in problems. But it's the exact opposite. Now, this is probably next to gravity. This is the next most important force, and it's called a normal force. So we use Fn, or we use just big N. Basically, what that is that's bad English, isn't it? Basically, what that is it's a reactionary force due to two objects that are touching each other. But if you've learned from math class, the word normal in math class means perpendicular. So it's always a force that's perpendicular to the plane of contact. So when you look at the book resting on the table, right? The book is resting on the table, so the Earth's gravity is pulling down, and so that's why there's a vector down called the weight. But the table's pushing up on the book with the same amount of force, right? So here's the plane of contact right here, right? The plane of contact is in the X, so the force is in the Y, right? This is perpendicular. This would be called a normal force. Here you're doing some sanding. You got a wooden desk here. You have this sanding block, right? Here's where their plane of contact is. Well, friction is this way, right? So the person is pushing this way down, but they're pushing in. This is kind of drawn wrong. And whatever this is, this wooden desk would then be pushing in this direction, right? And this is definitely not working. And so this normal force is perpendicular to the plane of contact. Again, there's no special equation to calculate the normal force, but other forces depend upon the normal force, like friction, right? The more things are in contact with each other, so the heavier something is, the molecules then become more intertwined and friction would then increase. And then, friction forces. So for friction, we have FF, or we have what I like to call the flamboyant F. A lot of times they'll write it like this with this little cursive small f. And there's an equation and it's on your formula sheet for friction. But now we'll talk, when we do Newton's second law, we'll talk more about the different types of frictions and how to calculate them and what does this guy mean, right? This is a coefficient of friction. It's a function of the types of materials that are in contact. So think about your tires on your car, on dry pavement, on wet pavement. There's a different coefficient of friction based on the type of tire you have and the kind of pavement you're driving on, whether it's concrete or just asphalt. Is the asphalt wet? Is it icy? Is it snowy? You have different coefficients. And so therefore you have different amounts of friction. It always opposes motion. So if the object's moving, it's always opposite. Friction forces could be drag from air, right? It could be the two objects in contact with each other. If an object is in water or a fluid, right, there's a resistive force. If you drop you drop something in some water and you watch it float to the bottom, there's a resistive force pushing upward against it. That would be a fluid resistive force. It always opposes motion or the want of motion, meaning like if this crate is sitting on this incline, right? So you see this guy's pushing this crate up the incline, so friction is opposite. If this guy wasn't there pushing this crate and he put it there or he just walks away, there's a good chance this crate's going to slide back down, but maybe it doesn't. Maybe there's enough friction to keep it stationary on the incline. And so this thing would want to move if this guy wasn't there. The crate would want to move down the incline. That means friction would be up the incline, right? So even if it's not moving, there can still be friction as a force that's holding it in place. But it would always be in the direction opposite the way the thing would start to move if friction didn't exist. So it always opposes motion or the want of motion. Now, sometimes you'll see spring forces. Sometimes your little toys when you're younger had springs in them. If you look at your garage door, you have up here, you have this thing. That's what makes the garage door go up and down. Otherwise it'd be pretty heavy. There's a spring there to help you. Here's a spring in your car. So there's a shock right here. That's that solid black thing, but around it you have this coiled spring, right? So we use those to make the ride a little more comfortable to absorb force. But it's due to the extension or compression of a spring. And it also has its own equation. We probably won't, it's on your formula sheet. We won't see this force or this formula really used until we get into probably harmonic motion. Generally, there's not a lot of spring problems in what we're doing right now. And so the K is a constant, X is how far you compress or stretch the spring. And there's a negative sign in the equation because it's always, it's the restoring force. Right, if you pull a spring apart and let go, what's it going to do? It's going to restore itself back to normal, right? Unless you go past the elastic limit. Like think of a slinky, you've played with those before. You've probably ruined a slinky because you've pulled it apart too far and now it won't go back. But the idea is it wants to go back, and that's why there's a negative sign in there. All right, so those are the main types of forces, right? You could have easily have gotten that from reading with the stuff that I had. But I want to spend the last little bit showing you how to make some of these force diagrams. Again, free body or force diagram or the free body force diagram. They're diagrams that we use to show the types of forces, the direction of the forces, and the size of forces acting on an object. So we make these vector diagrams. We just don't make them to scale. And notice that what I did here is I don't know if that's blue, and then you got I guess the red smaller, and then I made this paragraph bigger. Isn't that fancy? Right, the size of the arrow in the force diagram is supposed to reflect the magnitude of the force, is what I was talking about earlier. The direction shows you the direction of the arrow, shows you the direction of that force. And then we always have to label the force diagrams. We don't just draw a bunch of arrows around there, right? That's what third and fourth graders are going to do. We're going to label them, right? We're going to take it up a notch. And then you can draw it as a box. You can draw it as a small dot. Or if you're really artistic, you can draw the actual object, right? It takes time. Probably not going to do that, but that's up to you. Right? And then we look at the situation, and we use these force diagrams so that we can then set up our equations using Newton's first law, second law, or the third law. And then this just talks about what is the system. And so basically when we talk about a system, we're talking about the object and the force is acting on just that object, and nothing else exists. Nothing else in the world exists other than that object, right? And then the world around it, they call that the environment. Obviously, you would know that. So here you got this guy pulling a sled on some ice. You see that he's applying this force at an angle, right? And so we're going to have to break the force into its x and y component, just like we did with the Vx and Vy. But we would look at, so this is the system. It's the guy acting with the sled with the forces acting on it, right? And so you'd have to look at the situation and say, okay, what are all the forces acting on the sled? If you can't do that, then you're not going to be able to solve the problems, because that's the key. And that's why you have to know the different types of forces. What could be acting on it? Well, we know that he's pulling. So that could be, that we call it F. Well, that's a tension force. So maybe you want to call it tension. We know that the earth is pulling down on the sled. So the earth is always going to be pulling down on everything. So we're always going to have the force of gravity, and it's always down to the center of the earth. Well, this icy patch of ground is pushing back up, right? And so we have a normal force because this sled is in contact with the ground, and so the ground is pushing up. And then unless it tells us there's no friction, we know if he's pulling this thing to the right, then friction is to the left. And those would be the forces acting on the sled. And then you would make a force diagram, and then from the force diagram, we could calculate the different forces, right? Another example is probably the easiest one I can think of. Book rests on the table, so we always have the force of gravity. Again, you can label it Fg or you can label it W. The table pushes up. So in this particular thing, they called Ft as F of table. Really, this is, I would not, if I was the one that created this slide, I would change that to Fn or N, right, for normal force, because here's where they're in contact. It's a perpendicular force, right? And so it's a normal force is always a reactionary force due to objects in contact with each other. So what you can do, I don't know why it keeps goofing that up, right? So here your forces are balanced. We know the book is not moving, so it's in equilibrium. We'll talk about that on Thursday. It's the easiest case when all the forces equal zero, right? You know what equilibrium is from chemistry. Thermal equilibrium, chemical equilibrium, all that type of stuff. There's no net force, no resultant force on the book, because this force up equals the force down. When added together, they equal zero. Right, here's another one, or here's the same one. So like, as I said, I'm going to call them free body force diagrams, but this is a force diagram, right? A force diagram, if you read a textbook or you look at somebody else's video, basically they call it a force diagram when you draw the object and then draw the forces acting on it. And they call it a free body diagram when you draw a circle. The idea is the circle is supposed to represent the center of mass of the object. So think of your body, like we're symmetric across a vertical plane for the most part, not a horizontal plane, right? But where's if we were to take your body and figure out where is all of your mass centered at, right? It's somewhere around your belly button. So what we do is we say all the forces are acting on just that one point, because the effect of the forces on all the different aspects of the object is really not the same across the board. But that would make it really tricky for us to do any kind of physics problems. So what they're doing, no, it doesn't matter which one you draw. You can do it either way. You know, if you're short on time, you're like, draw a dot. If you're artistic, you're like, oh, I'm going to draw this, or you know, you can draw the object, then draw the object. But you don't have to do both. You can do one or the other. But it's the idea this dot is representing this book, all of the mass of the book concentrated at that one spot, right? Which would probably be the center of the book, give or take, would be that center of mass. But that's where that comes from. But again, it's one of those things that doesn't help us understand physics completely. Another example, here you have an object sitting on an inclined plane. What are the forces acting on it? Well, it's in contact with the inclined plane. So then I know that since it's in contact with the inclined plane, there's got to be a force in this direction, right? That would be a normal force. Well, I know the force of gravity. So for the force of gravity, you don't have to do it this way, but you will see, because again, the force of gravity is acting on the center of mass of the object. That would be the center of mass of this box. So normally people draw, or the textbooks will draw the force of gravity acting at the center of the box, right? And you'll label it FG or you'll label it W, not both, one or the other. But we only do that for the force of gravity. The normal force we would draw just in this direction, right? Label it Fn or N, right? And then what else do we have acting on it? Well, we know that this is going to slide down the incline, if it's going to slide at all, because there's nobody pushing up. So that means I know that friction is going to oppose the motion or the want of motion. And then generally what we do is we draw friction right here. Normally we would draw it like right there, right at the interaction. But sometimes that makes it so you can't see it. So it's okay to draw it a little bit above. And again, you can label it with FF or the little flamboyant cursive smaller f. But that's how you would do the force diagram. And I think this one's already drawn. Yeah. So if you see it, right, this is a force diagram. You don't have to draw it down here. You can draw it up here. But that would be the forces, and we're missing that label. That's a complete force. So if you don't label these things, it's like you didn't even do it. Right? Just think, we can go over to T. Clay Wood when we're back in school. We could go over to Dallas's 4th grade class and say, Dallas, have your class draw some arrows on these things, right? We would get, that's what we would get. We're 11th and 12th graders, so we want to be able to take it up one little notch from 4th grade. We want to be able to draw them in the right direction, but we want to be able to label them. That's the key, right? Same thing for if you're a skier, it's the same forces. Pretty much anything on an inclined plane, you got the same forces, right? And so you got a box on an incline, a skier skiing down a hill, that's an incline. Here you've got a pretty tricky one, just to show you how involved they can get, and it's already done for you, right? You've got the force of gravity, so it's always easy to start with that one. The force of gravity, you got this thing has weight, and this, because they have different masses, or maybe they have the same mass, but you have the normal force on that one. You have tension in this one, right? Because there's a cord connecting. We would do this activity if we were at school, right? That would be tension. This is a Newton's third law problem because there's two masses. So the third law deals with multiple objects moving together or not moving together, but they're connected by this rope. And so it turns out that this tension force pulling to the right on this one is the same tension pulling up on this one. And that's that Newton's third law pair. For every action, there's an equal and opposite reaction, which I know you've learned. Right? We have friction acting to the left. Oops. And that would be the force diagram for these two. So we would take this object and this object, we'd draw a force diagram for each object. We'd set up our equations and solve for whatever the unknowns are. Right? So at this point, normally in school, I have these stations where I have you guys walk around the room and do these together, but obviously that's impossible. So I'll just do a couple more with you just to get the idea. This should be really easy for people. If you invest a little bit of time required into it, it's going to make your life in this unit so much easier. I can't stress that enough because people blow it off. Be like, well, he's just drawing arrows. That's stupid. Yeah, I get it. But we'll talk in a month and say, see if you still think the same thing. So here you got friction, no motion. So it's not moving, you're pulling to the right, right? So you're pulling to the right. I would call that a tension force. Again, you can use Ft or T. So then what other forces? Well, if I'm pulling to the right, I know friction is to the left, but it's not moving. So I know that the force to the left has to equal the force to the right. I know that because it's not moving, right? So I would make this force equal to this force. You don't have to draw these lines, but you should make these two vectors look similar in size, right? If you drew it too big or too small, that would imply that it's accelerating and the forces aren't balanced and it's moving. Well, we know this is always one you're going to draw, right? The force of gravity, but it's not moving down, right? Because there's something in its way, and that is the floor, and the floor is pushing up with the same amount of force that the earth is pulling down. And so this force is equal to this force, right? And that's a force diagram or a free body diagram, right? And if you drew the box and you drew the forces, then that's typically what they call a force diagram, right?
Would
Ignore
you not
this.
include the friction?
Right there, here's friction.
Oh, okay. Okay, my bad.
Yep. Friction's to the left because we're pulling to the right. So if it's going to move, it would want to move to the right. Friction's going to oppose that motion to the left. Friday, maybe we get some snow, right? So maybe you want to go sledding if we get enough of it. So imagine he's on a sled. There's friction. He's moving down the incline at a constant velocity. So this is going to be important whether or not we're moving at a constant velocity or accelerating. That's going to determine what our forces add up to. But again, so this is the first one. We know we're always going to have a force of gravity. Now, again, we don't draw the force of gravity this way. We draw it to the center of the Earth, right? So the center of the Earth is taken to be like that. Why does it do that? Just ignore these lines. I don't know why something is going on with this X pen thing. But the force of gravity is always down. We know there's a normal force, right? Perpendicular to where his butt and feet are in contact with the surface of this incline. There's friction. So if he's going to slide down the incline, we know that. So here, this is why you might not want to draw it right here because it would be hard to see. And I would just draw it above. It's getting worse, right? Force of friction is up the incline. Is there any other forces acting on him? Well, there's not, right? So you got to look at it and say, what else could be acting on? There's no tension, there's no compression, there's no springs. And so it's just the normal force, the frictional force, and gravity. Now, what would happen here, and again, we wouldn't be able to really do this without a protractor and a ruler, is that if I was to take all three of these forces and add them together, they would have to come out to be equal to 0 because it's moving at a constant velocity. But we're not worried about that yet, right? We're just worried about, can we make the force diagram. Let me see what else I have. All right, we only got a minute left, so I'll just do one more. And this is what your homework is. Our bell work for Thursday is simply going to be doing these, right? And so what I want to see is you to make a picture, or draw it on the picture that's given. That's fine. So there's friction. He's moving up the incline at a constant velocity. So we know that we're pulling in this direction. You could call it the pulling force, FP. You could call it F, FT, tension. You could just call it F, if that's what you wanted to call it. Again, we know there's the force of gravity that's straight down, even though that's right. We know there's a normal force. So there's friction. So now he's moving up the incline. So we know that friction is this direction, right? Is there any other forces? No. And if I was to take this, and this and add them together, they'd all add up to 0 because it equals a constant velocity, or it's causing a constant velocity, which means we have balanced forces, which is what we're going to learn about with Newton's first law. Any questions on that? Now you can see really what you need to know is the types of forces. Because if you don't know what the normal force is, or if you don't know what tension is, then you're not going to be able to make the force diagrams, and then you're not going to be able to do the next step, which is solve the problem. And these, all I have left here are just a bunch that we'll do some more of these. You can see I've got millions. And a bunch of these are on your homework. Oh, does this work? No, it doesn't work. Well, that's depressing. Does this one work?
Remember, the force will be with you, always.
Yeah, at least the ending worked. That's good. Any questions?